We're going to go next to Kula Bio, and I see that Bill and Sam are online. Um, so I was quite struck when I first spoke to Bill. I was a little slow on the uptake, but finally I got it towards the end of his presentation that he could be revolutionary, and that his biologic fertilizer, nitrogen fixing fertilizer, was potentially groundbreaking. So I'm going to not say more about it than let Sam introduce Bill, and then have Bill make his presentation.
Awesome. Thanks, Howard. I'm Sam Snepsteiner. I'm a partner at VC firm Innovation Endeavors, and happy to introduce Bill and Kula Bio today. So that would be helpful to share some of the context in which I think I got excited about Kula. So I've been interested in sort of the intersection of ag bio and climate or sustainability for the past couple of years. So on the ag bio side, this is largely, how do we take cutting edge computational approaches or bioengineering approaches, often that we first see in the life sciences, but apply them to ag. And then on the sustainability side, I think this could be everything from reducing emissions to actually transitioning agriculture to be a carbon sink, to sort of the broader mitigation of the negative ecological impacts of agriculture. So at that intersection, synthetic nitrogen is, of course, critical ag input, and a dirty one, from the Haber-Bosch process to sort of runoff coming off of fields. So one we've been interested in, and there are obviously lots of folks working on this problem in various ways. Bill will definitely describe this in sort of more detail and more effectively than I will, but at its core, Kula is creating fertilizer through a nitrogen fixing organism that has really exciting advantages that we're quite keen on, in terms of, I think, a few things. So one is duration, which we know is often a concern with biologics. They've got sort of a longer acting microbe due to some energy storage work they've done there, that also enables them to deliver a much higher quantity of nitrogen, which is exciting. The second is that it's crop agnostic, especially compared to some of the genetic engineering or seed treatment approaches we've seen elsewhere. And then lastly is that there's actually room for this to be a carbon sink. So like I talked about, they're definitely evading a lot of emissions through the Haber-Bosch process, but they're actually using carbon as a feedstock in micro production as well. So a bit of a double whammy on the sustainability side, which is exciting. So I'll let Bill take it away and share more.
Thank you, Sam. Appreciate that. And thank you, Howard. Let me share my screen. So my name is Bill Brady. I'm the co-founder and CEO of Kula Bio. And we're a biologically derived nitrogen fertilizer company. We started the company in 2018, and I co-founded it with Dr. Dan Nocera from Harvard University. And so what I've put together today is just something to try to take you through the problem we're addressing, our technology solution, and then tell you a little bit about how we've done out on the farm since we've started. So let's just start with the nitrogen problem. So what this chart shows you, on the vertical axis is the global population, on the horizontal axis is time. And we have about 7 billion people in the world today, and about half of them get their nitrogen, which, by the way, we all need nitrogen to grow. And we get it from either eating the plants who take it up, or from the animals who eat the plants. But about half of us get our nitrogen from naturally occurring sources. The other half of the population gets it from synthetic nitrogen. And the problem here, as I'm going to show you in a second, is synthetic nitrogen is completely unsustainable, and we're going to need a lot more of it as the population goes to 10 billion. So the synthetic nitrogen fertilizer problems is really twofold. Number one, for every pound of nitrogen you make with this process called the Haber-Bosch process, you produce about 4 tons of CO2. The other problem is, of all the nitrogen fertilizer put on the soil, synthetic nitrogen, about 50% of it runs off. It ends up in our waterways. So it's a huge problem. Even when you get to organic sources of nitrogen fertilizer, they've got issues as well. Number one, they're really expensive, about $3 to $9 per pound of nitrogen. There's the pathogen risk. Most of, for example, the lettuce recalls we've all seen and heard about come from the nitrogen, organic nitrogen fertilizer. And then finally, there's a timing issue. If you want organic nitrogen to get to your plant, you've got to put it down 6 to 9 months in advance and have it decompose. So we're breaking those choices, those bad choices that the farmers have to make. So let me tell you a little bit about how we do it. So the first thing, microbes in agriculture is not a new idea. The problem is most microbe and most microbial approaches at this have the problem of the microbes, once they get in the soil, either have to compete with existing microbes for energy and food or borrow it from the plant itself. So this is not a terrible thing, but the microbes only live a matter of hours, maybe up to a day. And so what Kula does is we give these microbes their own independent source of energy before they get in the soil. And our microbes today last for 2.5 weeks. So if these microbes can live for 2.5 weeks, all of a sudden, the quantity of nitrogen that they can deliver gets significant. And if you divide the cost by that quantity, the cost per pound of nitrogen gets really, really competitive. So here's how we do it. And believe me, I won't go deep into the biochemistry here, but I just want to give you a sense of what we do. All the way on the left side in that tank, that represents our bioreactor. Into the bioreactor goes water, microbes, and a nutritional salt mix. And in the first phase of it, we build up the microbial density. We just get these microbes to multiply like crazy. And when they get to a certain microbial density, we cut the nutrition. Now under stress, we feed the microbes hydrogen from the water and CO2 from air we pump in, ambient air we pump in. The microbe metabolizes the hydrogen and CO2 to create this energy storing material. So to oversimplify it, think a little bit of a bear prior to hibernation. And so we basically fatten these microbes up, and then into the soil they go. And once in the soil, they start to draw on that source of energy and express a nitrogenase enzyme, which has the capability to fix nitrogen from the air. By the way, the air is 80% nitrogen from the air, and deliver it to the soil. And then it's picked up by the plant. So that's the general flow of how we get the product to the plant. So I'm going to tell you more here about our nitrogen product and approach, but one thing I just wanted to mention. We picked nitrogen first for a lot of reasons, maybe some obvious, but this idea of extending the life of beneficial microbes goes far beyond nitrogen, we believe. And I just listed a couple of the other things we've just dabbled in on this chart, but you can think of any microbe that can benefit from a longer lifespan. And we think our technology can be applicable. Okay, let me talk a little bit about the field trials. So this, first of all, this picture, that's the product. It looks and has the consistency of orange juice. And one of the really important things when we talked to the farmers, they told us 3 things. We're not going to pay you any more money. We're not going to do anything different. and we're not going to buy any new capital equipment. So you got to make your product fit into those parameters. And so that was a big part of our design of the product. And the state of the product form today, whatever the liquid distribution is on the farm, they can use that to distribute our fertilizer. So the summary on our trials, a couple of key points. We've replaced between 50 and 100% of synthetic nitrogen in each of our trials. I'll show you a little bit more data on that on the next slide. We have seen, very interestingly, early fruit ripening on tomatoes and strawberries. And then finally, we run 4 100-liter bioreactors to supply this product. We basically run them every day because the demand for the product is higher than our capacity. So here's the summary of the field trials. All of these trials were on commercial farms or greenhouses or commercial greenhouses. We've done numerous other type trials, but these were the major ones. So you can see in lettuce, we did 4 different regions, and we replaced 50 to 80% of synthetics, and the crop yield was 100%. So equal yields, 50 to 80% replaced. In corn, which we did a sweet corn trial in the Northeast, a similar result, 50% replaced at equal yields. Tomatoes, which we did both outdoors and in greenhouses, also 50 to 80%. Interestingly, tomatoes had, in most trials, are over 100%, up to 150% yield. Strawberries, the same. Most of this work was in California, some in greenhouse. And then we did work on turf as well. And a little bit harder to measure here because there's not yield data, but aesthetics and soil quality were as good or better than synthetics. And then one last interesting point, we continue to do significant work with the International Fertilizer Development Company in Alabama. And I just want to point out one piece of this work has been quantifying nitrogen runoff. And we have seen dramatic decreases in the runoff from soil with our product relative to urea or synthetic fertilizer. So this is a picture of our costs. It's maybe not the most exciting thing to always talk about, but in my experience in industrial technologies, if you don't have a cost position, you are going to get disappointed at some point in time. So what this shows on this chart, on the left side of the chart, left of that vertical dotted line, these are the different organic sources of nitrogen and what the farmer pays on a per pound of nitrogen basis. It's a little bit counterintuitive to think of these materials, compost, fish meal, poultry manure, as expensive, but they are so low in nitrogen content and take so much work to get on the field, it ends up costing the farmer quite a lot. On the right side are cost figures. So the left side is what the farmer pays. The right side of that vertical dotted line are cost figures. And so for synthetic nitrogen, it costs roughly 25 cents per pound of nitrogen to produce, manufacturing costs. This fluctuates a little. It's largely driven by the price of natural gas. In Kula Bio, our Kula end product is 10 cents per pound of nitrogen. And just if you think back to, a lot of people are surprised by the low cost point for the biologic, but if you think back to our inputs that I described earlier, it was water, microbes, salt, and air. And so we really start with a very, very low cost inputs. And then our job is to drive that density up, which is basically increases throughput. So that's our cost. And obviously we can do very well in the organic side of the business, but can also compete on the very big synthetic piece. The last piece I just want to describe is our carbon footprint. So this page looks at a 400-acre farm, which uses what I would call a typical amount of nitrogen fertilizer. And so on the right side, this is the carbon footprint if you use Haber-Bosch produced synthetic nitrogen. I mentioned earlier, Haber-Bosch, you produce 4.2 pounds of CO2 for every pound of nitrogen. This farm would use 26,000 pounds of nitrogen, and so you emit 109,000 pounds of CO2 every year just from the nitrogen fertilizer on that farm. On the left side of this chart is the Kula Bio, Kula N picture. So in our process, we actually consume roughly a half pound, this says 0.6 pounds of CO2 per pound of nitrogen. So again, remember those inputs. We had microbe, water, salt, and then the ambient air, which includes CO2, which the microbe consumes, goes into the soil, uses the carbon for energy, and then just dies and is effectively sequestered. So on our carbon accounting, you would not emit, but sequester 16,000 pounds of CO2 on this farm annually. So it's, aside from solving the runoff problems, we've got a terrific carbon footprint as well. So I will stop there, and I would be glad to answer any questions.
So, Bill, you have a couple questions in the chat, but does Brett or Scott want to just ask the questions directly, or do you want us to read them for you? Brett? Scott? Go ahead, Scott.
I'm happy to ask directly. Thanks, Bill. That was really interesting. Just a question for you in terms of other benefits, and you mentioned a lot, but in terms of flavor and taste, any benefits that the growers saw in the corn, the tomatoes, etc., when they use this versus synthetic nitrogen? Did it do anything else to the quality of the fruit and veggies?
Not that we've seen yet. So we've, the farmers did their work. We did bricks testing and stuff like that. But I would say, by and large, I would have to report equal to synthetic fertilizer.
Great. And then my second question to that was, what about, did it improve the overall soil health in terms of diversity of the microbiome of the soil? So you're introducing some new microbiome. Did it improve the overall health of the soil over time, or has it not been long enough to determine that?
Yeah, I think it's not been long enough to determine that. I think it's probably more relevant over a season or two. But the soil organic carbon content is up. There's more food for all the beneficial organisms left over, and we fully expect over time that we will see. And as you know, synthetic nitrogen works in the opposite direction.
Yes.
Yeah. So
thanks.
Brett's question is, what is the shelf life and stability of your product and the effective colonization rate?
Yeah, so I'm not sure I have numbers for you on the colonization rate, but on the shelf life and stability, we have just started that work. So the microbe, as it is, has about 3 weeks shelf life at room temperature without any deterioration. Under mild refrigeration, 40F, it lasts for months. Now, of course, we want to avoid that. But we had been focused on the dosing and efficacy and also the bioprocessing. And we're just getting to the shelf life, which we know is a very important issue. I do expect that we are going to be able to apply many of the well-known methodologies to extend shelf life to this product.
Last question from Ted Barbers. He asked the same question regarding nutritional values. Does your product have any impact on the nutritional values of the crops that were raised or the produce that was raised?
We haven't seen it yet. We haven't seen it yet. Again, this might be something over time as the soil quality increases that we'll see, but at this point, I really don't have anything to report on that.
Roy, do you want to ask your question live, or do you want me to read it?
Yes, I'm more than happy to ask directly. So the two questions. One is whether you try to install your technology to the other region than the United States, you need to adjust within the type of soil. That's question number one. The other question is that are you considering to have another revenue stream, such as a carbon credit throughout with installing your technology?
Yeah, thanks, Roy. On the other soils, other regions, we have had a lot of interest from China and the largest player in China. And we've had a lot of success in a wide range of soils, including some pretty poor soils. It is interesting, our microbe goes into the soil and is really kind of an independent actor. It's self-contained, it's got its own source of energy, does its thing, and then dies. So it has a lot of tolerance. And the starting bug, which is a Xanthobacter, is a very, very robust microbe. It is not genetically modified. So, some of the difficulties, some of the other, let's say, well-known names trying to do this have with the finicky nature of their bug, we don't have. So, pretty good. We're pretty confident that as the soil gets worse, our story might get better. And then, yes, we are working on the carbon credit system. I have talked to more people about what the value is going to be, how to measure it, how deep the carbon has to be. And, it's a bit of a mess, as many of you know. But we got a great story, and I think we are going to have a carbon revenue stream as well.
Hey,
Okay.
Bill, we got to run here. We got to go back to the main session, but one quick last question, just throwing a bomb a little bit here. So, your story is so good. I mean, it's like everything seems to line up. Everything is good. So it's almost like it's too good to be true. So what is the fly in the ointment? I mean, what is it that makes you stay up at night?
Yeah, to be honest, it works. The technology works. We're making good progress on the bioprocessing and manufacturing. A lot of good, hard work to be done on both of those areas. I think the thing that keeps me up most at night is how do I get the farmers to say yes? Mm-hmm. How do I ultimately get the farmers to say yes? How do I get the distribution networks, the influencers, the crop advisors all lined up so that the farmers say yes to this? And that we're working on it, but that is a hard problem. But Howard, that's to me is the biggest challenge here with this company.
Yeah, makes sense. Terrific. That's very exciting, Bill. Thanks so much for the presentation.
Thanks for having me. Appreciate it.